You're trying to get up to speed fast, right? Understand the core ideas without wading through tons of jargon.
Yeah, that's the goal here.
Great. So today, we're diving into something really fundamental in dentistry, how they capture all the details of your mouth using impression materials.
And then how that gets turned into a solid model using gypsum products.
Exactly. You shared some excellent sources of video and some detailed notes.
And our mission really is to pull out the essentials from these. So you'll get why these steps are so critical for, well, pretty much everything from diagnosis to making crowns or dentures.
Okay, let's break it down. The whole thing kind of rests on two main stages. First, taking what's called a negative impression. Think of it like making a mold of something.
Right, like pressing your hand in Play-Doh, capturing the shape, but inverted.
And then that mold gets filled with gypsum material, which sets hard, giving you a positive copy, the dental cast, the model.
And that model has to be accurate. It's the absolute foundation for planning treatments, making restorations.
Crowns, bridges, dentures, all that stuff relies on a good model. So let's start at the beginning. How do they get that initial mold? What makes a good impression material?
Well, the sources highlight a few ideal properties. First off, it needs to be fluid enough, to flow into every tiny nook and cranny, get all that detail.
Makes sense, but
Yeah.
it can't be too runny, right? You don't want it dripping everywhere.
Exactly. It needs enough body, enough viscosity to stay put in the impression tray while it flows around the teeth and gums.
Okay, so that's the consistency. What else?
Then it needs to set. Turn into a rubbery or maybe a rigid solid pretty quickly. The ideal time mentioned is around 7 minutes or less.
Nobody wants that tray stuck in their mouth for half an hour.
Definitely not. And crucially, once it's set and removed, it absolutely has to hold its shape. It shouldn't distort or tear, especially when being pulled over undercuts.
Those little inward curves on teeth.
Yes, exactly. If the material stretches and doesn't spring back perfectly, or if it tears in a thin area, the accuracy is lost.
And that ties into dimensional stability, I guess. It needs
Yeah.
to stay the same size.
Absolutely critical. The
Okay.
lab might not pour the gypsum cast immediately, so the impression can't shrink or expand while it's waiting. Any change means the final crown or whatever won't fit properly.
Right. And, of course, it needs to be affordable and, well, safe to put in someone's mouth. Biocompatible.
Can't forget those practicalities.
Okay, so with those ideal properties in mind, the materials fall into two big camps. Inelastic ones that set hard and rigid.
And elastic ones that have some flexibility, like rubber.
Let's look at the inelastic ones first. Maybe a bit more historical now, but good context. Like impression plaster, plaster of Paris.
Yeah, impression plaster. It's based on beta-calcium sulfate hemihydrate, which is interesting because that's the same base chemical as the gypsum used for the casts.
Oh, right, so it's chemically similar.
Very similar. Its use was pretty limited, mostly for impressions of soft tissues where there weren't big undercuts, like for making, say, complete dentures. The main issue was its rigidity.
Because it would just snap if you tried to pull it off curly teeth.
Exactly. It could fracture easily in those undercut areas, but even then, they tweaked it, added things like potassium sulfate to control setting expansion.
And borax to slow the setting down, give the dentist more time.
Right. And sometimes pigments, like alizarin red, just to make it easier to see against the white gypsum cast later on. Disinfection was possible with sodium hypochlorite.
And it's not totally gone. Still used sometimes for implants.
In very specific scenarios, yes, sometimes with transfer copings, maybe combined with resin composite or acrylic.
Okay, what came next? Impression compound.
Impression compound, that's a thermoplastic material, softens with heat, hardens when it cools. Came in sheets and sticks.
Two types, right? Type I for cavities, type 2 for making trays.
Correct. Type 2, the higher fusing one, was often used to make those custom trays for other impression materials later. You'd soften it with heat flame for the sticks, warm water for the sheets.
Sounds a bit fiddly.
Yeah.
What was it made of?
A mix of things. Waxes, thermoplastic resins, fillers for body, colors, sometimes shellac or stearic acid to improve how it handled.
Any downsides?
Oh yeah. Overheat it and it could get brittle, and dimensional stability wasn't great if it didn't cool thoroughly. The advice was always to pour the cast within an hour or so.
And disinfection.
Alkaline glutaraldehyde could be used, but you had to rinse it well and pour the cast pretty much immediately.
Okay, moving on. Zinc oxide eugenol. ZOE.
Ah, ZOE. A real workhorse material for a long time. Very versatile, used for edentulous impressions, people with no teeth.
But also surgical dressings, bite registrations, temporary fillings, even root canal sealing.
Wow. And denture relining, too. It's a two-paste system. Zinc oxide in one, eugenol, that's from cloves, in the other.
Eugenol. Doesn't that have a strong smell?
And potential irritation.
It does. Sometimes oil of cloves was added to mitigate irritation. The reaction forms zinc eugenolate, and interestingly, moisture actually speeds it up.
So saliva helps it set faster. In a way, yes. They added fillers to control the consistency, and it came in hard type 1 and soft type 2 versions, setting in maybe 10-15 minutes.
Big advantage.
Very little shrinkage, good dimensional stability. Could also be disinfected with alkaline glutaraldehyde. Still has its uses today, definitely.
Okay, so that covers the main inelastic ones.
Okay.
Now, for the elastic materials, the ones that really improved accuracy, especially with undercuts.
Right. And these split into two groups. The elastomers, which are synthetic polymers.
Synthetic rubbers, basically.
Pretty much. And the hydrocolloids, which set differently through a sol gel process. Let's tackle the elastomers first.
Elastomers, so they stretch and bounce back. That's the key.
That's the defining feature. Chemical cross-linking creates that elastic recovery. Absolutely vital for pulling impressions off complex tooth shapes without distortion.
And they come as 2 parts base and catalyst in different thicknesses.
Exactly. 2 components you mix to start the setting.
Yeah.
And various viscosities, extra low, medium, heavy body, even putty, each used for different things.
Like thin stuff for fine detail, thick stuff for support.
Precisely. The thin washed materials capture the surface detail. The heavier putty materials provide bulk and push the wash into place. First up, polysulfide.
Polysulfide. The video suggested this one's a bit older school now.
It is, but worth understanding. Base is a polysulfide polymer. Catalyst often had lead dioxide, though newer ones might use other catalysts. Setting starts on mixing.
And temperature and moisture speed it up. Less working time if it's hot or humid.
Correct. But the really big thing with polysulfide was the byproduct. Water. Water. How does that affect it?
As that water evaporates after you take the impression, the whole thing shrinks. Dimensional instability.
Okay. So you needed custom trays to try and get an even thickness.
That was the preference, yes.
Yeah.
To minimize distortion. On the plus side, it's the most flexible, least stiff elastomer. So easier to remove from undercuts sometimes.
But you couldn't reliably pour multiple models from one impression.
Generally not recommended due to that potential distortion. It did have good tear strength, though. Okay. Next was condensation silicone.
Condensation silicone. Base is polydimethylsiloxane, catalyst usually stannous octope. Also sets by cross-linking.
But a different byproduct this time.
Yes, ethyl alcohol. And just like water in polysulfide, as the alcohol evaporates.
It shrinks. Same problem, different chemical.
Exactly. Significant dimensional instability again, limiting its accuracy over time.
Which leads us to addition silicone, also called PVS or VPS. The video seemed quite keen on this one.
Yes, polyvinyl siloxane or vinyl polysiloxane, big step forward, sets via addition polymerization.
And the byproduct.
Hydrogen gas. But here's the key. The gas release doesn't really cause dimensional change in the impression itself. Much more stable.
But the gas can cause issues if you pour the model too soon. Little bubbles.
Tiny pinpoint voids on the gypsum cast, potentially. That's why you usually wait maybe 30 minutes or so before pouring. Let the gas dissipate.
Another thing mentioned was hydrophobicity. Silicones don't like water.
Naturally, yes. Which isn't ideal in a wet mouth. Manufacturers add surfactants, tiny molecules to make them more hydrophilic, better able to wet the surfaces.
But keeping the area dry is still best.
Definitely helps capture the finest details. And a crucial point, sulfur from latex gloves.
Oh yeah, the video stressed that. It stops it setting properly.
It inhibits the setting reaction, especially right at that critical tooth impression interface. So no touching prepped teeth with latex gloves right before the impression.
Got it. Properties-wise, addition silicone is.
Generally good handling, quite tough, not super flexible, but good tear resistance. And crucially, almost no setting shrinkage. Very dimensionally stable.
Okay, what about polyether?
Polyether, different chemistry again. Base paste has a polyether polymer filler plasticizer. Accelerator paste has an alkyl aromatic sulfonate initiator. Sets via ring opening polymerization.
How does it compare?
Generally offers excellent dimensional stability and elastic recovery, maybe even better than addition silicone in some respects. Good for multiple tours.
And you can use standard trays.
Often works well with stock trays, yes. It's considered perhaps the most dimensionally stable elastomer overall, another plus.
Right.
It's inherently less hydrophobic than the silicones. Wets tissues better.
So maybe better detail capture in slightly moist conditions.
Potentially, yes. Lower contact angle with water. And it stands up well to disinfection with alkaline glutaraldehyde.
Right, so that covers the elastomers. So now the other elastic group, hydrocolloids, they set via Solgel transformation. What's
Here's a
that?
simple version. Starts as a liquid solution, solalater, then transforms into a semi-solid jelly-like state, gel. This can happen via temperature change or a chemical reaction.
And the two main types in dentistry are agar and alginate.
Correct. Agar is reversible, alginate is irreversible.
Let's start with agar, from seaweed, mostly water.
Exactly. Polysaccharide from seaweed, water is the main component. Borax is added for gel strength.
But borax messes with gypsum setting.
It can, so potassium sulfate is also added to counteract that effect.
And using agar sounds involved. You need special equipment. Boiling, storing, tempering.
Very technique sensitive. You boil it to liquefy, 100 degrees C, store it warm, around 65 degrees C, and then temper it down, around 45 degrees, before putting it in the mouth using special water-cooled trays.
45 degrees, still warm but bearable, I guess. Then cool water circulates through the tray to make it set.
Yes, cool water, 1821 degrees C, speeds up the gelation. It takes a few minutes. The big advantage was potentially very high accuracy.
And it's reversible. You can melt it down and reuse it.
Theoretically, yes, because it sets based on temperature, but the whole process is cumbersome, so it's not used as much now.
Okay, so on to alginate. Also from seaweed, but irreversible.
Right. Once it sets chemically, that's it. Main ingredient is sodium or potassium alginate.
And lots of other stuff mixed in. Fillers like diatomaceous earth for strength and texture, zinc oxide.
Yes, and calcium sulfate dihydrate, that's the reactor, provides calcium ions to cross-link the alginate chains and form the gel.
And chemicals to control the speed. Retarders like sodium phosphate.
Exactly, to give workable setting time. Sometimes potassium titanium fluoride is added too, thought to improve the surface of the gypsum cast poured against it.
And water temperature is really critical for alginate setting time.
Hugely critical. Warmer water makes it set much faster. Room temp water, around 20 degrees C, is usually recommended. Hot weather means you might need chilled water or cooled bowls.
Trays. Perforated metal is best.
Mm-hmm.
Or adhesive for plastic ones.
Perforated trays give good mechanical lock. You need adhesive for smooth plastic trays, and you need decent thickness, at least 3 millimeters everywhere.
And leave it in the mouth a few minutes after it seems set, then snap it out.
Yes. Allow 3 minutes post-ductility for strength. And a quick, sharp removal reduces tearing and distortion.
Storage is tricky too. It's mostly water, so it can dry out or swell up.
Big time. Needs to be stored in 100% relative humidity, like a sealed bag with a damp paper towel, but not soaking wet until poured. ASE is best.
Yeah, disinfection. Short immersion, maybe 10 minutes max.
Typically, yes. Solutions like dilute bleach or specific disinfectants, but brief contact to avoid dimensional changes.
Accuracy-wise, alginate is good, but maybe not for super fine detail like crowns. More for study models, partial dentures.
Generally, yes. Good accuracy for many things, but elastomers usually capture finer marginal detail needed for fixed prosthodontics.
Okay, let's recap some handling points for these materials. For elastomers, you said custom trays are best for polysulfide.
Because of its potential instability, yeah, helps get even thickness. But stock trays often work fine for polyether and addition silicone.
And polysulfide is most flexible. But PDS and polyether have better stability and recovery, meaning you can pour multiple casts.
That's the general idea, yes. Their accuracy holds up better.
Mixing. You can hand mix, use static mixing guns, or dynamic mechanical mixers.
All are options. Static mixing is common for cartridge systems, gives a consistent mix. Dynamic mixing aims for an even more homogeneous, bubble-free mix, especially for monophase materials.
And techniques like putty wash or monophase are used depending on the situation.
Correct. Putty wash uses a thick putty and thin wash for detail. Monophase uses one consistency. Material properties like shear thinning, flowing better under pressure help them adapt.
Stability factors again. Polymerization shrinkage, thermal changes, water absorption. Polyether and PVS win here.
Generally, yes. They show the least overall dimensional change over relevant time periods. Disinfection is usually fine with glutaraldehyde, but avoid long soaks.
And tear strength. Polysulfide was highest, but tear energy is a better measure.
Tear strength is just the force to start a tear. Tear energy considers the energy needed to propagate the tear. It's a more complete picture of toughness. Polysulfide does resist tearing well in thin areas.
Now for hydrocolloids, specifically alginate, water-powder ratio is king.
Absolutely critical. Follow manufacturer instructions precisely. Add powder to water. Mix vigorously, figure-8 motion, avoid whipping in air, weigh the powder if possible.
Clean bowl and spatula matter too.
Yes, any leftover set, gypsum or alginate, can accelerate the set.
Impression taking.
Hmm.
Perforated metal or adhesive on plastic. 3 mm minimum thickness. 3 minutes after gelation. Snap removal.
You've got it. Those are the key points for alginate impressions.
Storage. Cool, dry place for the powder. 100% humidity for the impression until poured.
Essential for stability.
Gypsum compatibility. The potassium sulfate in alginate helps counteract any setting inhibition.
It does. Helps ensure the gypsum sets properly against the alginate surface.
Disinfection. Rinse. Short immersion, 10 mins max. An appropriate solution.
Yep. Balanced disinfection with minimizing dimensional change.
Accuracy. Good for many uses, less so for high-precision fixed work compared to elastomers.
That's a fair summary. Alginate is fantastic for study models, orthodontic models, partial denture frameworks, things like that.
Okay, we've got the negative impression. Stage 2, making the positive cast with gypsum. What exactly is gypsum chemically?
Chemically, it's calcium sulfate dihydrate, KSO4.2H2O, 2 water molecules per calcium sulfate molecule. It's mined as a mineral.
But the powder we use isn't dihydrate, it's processed.
Right. They heat the mined gypsum, a process called calcination, usually 110, 130 degrees C. This drives off about 3/4 of the water, leaving calcium sulfate hemihydrate. That's the powder.
So hemihydrate is the powder, then you add water back.
And the chemical reaction reverses. The hemihydrate dissolves, reacts with the water, and recrystallizes back into the stable dihydrate form, interlocking into a hard mass.
And that setting reaction gives off heat. Exothermic.
Yes, you can often feel the model warming up as it sets. It's the reverse of the calcination, which needed heat input.
There's a theory for how it sets. Dissolution precipitation.
That's the widely accepted model. The hemihydrate powder dissolves in the mixing water until the water is saturated. Then, because the dihydrate form is less soluble, it starts to precipitate out as crystals.
And these crystals grow and lock together.
Exactly. As dihydrate precipitates, more hemihydrate dissolves to keep the solution saturated, allowing more crystals to form and grow, eventually creating that solid interlocked structure.
Now, a key thing with gypsum is setting expansion. It actually gets slightly bigger as it hardens. Why?
It seems counterintuitive, but yes. It's mainly due to the outward thrust of the growing dihydrate crystals as they intermesh and push against each other during setting.
So the crystals themselves might be denser, but the way they arrange themselves causes expansion.
That's the idea. The growth pressure forces the whole mass to expand slightly.
And there's normal expansion and hygroscopic expansion.
Right. Normal setting expansion is what happens when it sets in air. Hygroscopic expansion happens if it sets while immersed in or in constant contact with water.
And hygroscopic is more expansion.
Significantly more, yes. The continuous supply of water allows the crystals to grow larger or perhaps differently, leading to greater outward pressure and thus greater overall expansion.
Why would you want more expansion?
Good question. It's used deliberately in some techniques, particularly for casting metal alloys. Many alloys shrink when they cool from molten to solid.
So the extra expansion of the gypsum mold helps compensate for the metal shrinkage.
Precisely. By using hygroscopic expansion in the investment material, which is a type of gypsum, the final metal casting ends up closer to the intended size.
Clever. Okay, what about the strength of this set gypsum? That must be important for a working model.
Absolutely vital. Compressive strength is key, how much squeezing it can take. We talk about wet strength.
When it's just set and still has excess water.
Yes, also called green strength. It's lower then. Dry strength is achieved after all that excess water evaporates, allowing the crystals to lock together more effectively. Dry strength is significantly higher.
And the water-to-powder ratio is the big controller of strength.
Huge factor. More water means more porous structure, fewer crystals per volume, therefore weaker gypsum. Less water means a denser, stronger structure.
But you can't use too little water either.
No, if the mix is too thick, it won't flow properly and the reaction might be incomplete, actually reducing strength. You need the manufacturer's recommended ratio.
Does mixing time matter? Spatulation.
It does. Proper mixing ensures all particles are wetted and react. Up to a point, more mixing increases strength, but overmixing can start breaking down the newly forming crystals and weaken the final cast.
And additives like accelerators or retarders, can they affect strength?
They can sometimes slightly reduce the ultimate strength. Yes, it's a trade-off for controlling the setting time.
Okay, so different needs led to different types of gypsum. 5 main types, according to the ADA spec.
That's right. Type I is impression plaster. Beta hemihydrate, modified for impressions, rarely used now.
Type 2 is model plaster, also beta hemihydrate. Weaker.
Yes, standard plaster. Used for things like flasking dentures, where high strength isn't the priority. Often white. Beta hemihydrate particles are more irregular, need more water.
Then type 3, dental stone. Stronger.
Much stronger. Made from alpha hemihydrate, calcined differently. Particles are more prismatic, regular. Needs less water, so it's denser and stronger. Used for diagnostic casts, denture models.
Alpha hemihydrate is key for strength then. What's type 4?
Type 4 is high-strength dental stone, or dye stone. It's a modified alpha hemihydrate. Even more regular, denser particles, needs even less water.
So it's very strong, very hard, and doesn't expand much. Ideal for making dyes for crowns and bridges.
Exactly. High accuracy, high surface hardness, resists scratching, minimal expansion are crucial for dyes. High Rockwell hardness.
And finally, type V, high strength, high expansion.
Another modified alpha hemihydrate, highest strength but also deliberately formulated for higher setting expansion than type 4.
Why the higher expansion again?
To compensate for the greater shrinkage of some newer casting alloys, especially base metal alloys used for frameworks.
But maybe not ideal for small, precise things like inlays because it might make them too tight.
That's the concern, yes. The expansion might be too much for highly precise, smaller restorations.
Got it. Now, practically using gypsum, storage is important. Keep it dry.
Absolutely. It's hygroscopic, absorbs moisture from the air. Humidity above 70% can start setting the powder in the container. Store sealed in a dry place.
Measuring, use a balance for powder, cylinder for water, not scoops.
Weighing powder is much more accurate than scooping by volume. Pre-weighed packets are even better for consistency. Measure water carefully.
Mixing. Water first, then sift powder in. Mix vigorously for about a minute.
That's the standard hand mixing technique. Use a clean, flexible bowl and stiff spatula. Avoid whipping air in.
Vacuum mixing is better for strength and fewer bubbles.
Definitely. Removes entrapped air, leading to a denser, stronger, smoother cast. Mix briefly by hand first, then maybe 20-30 seconds under vacuum.
And vibration helps get bubbles out and flow the gypsum.
Yes, high frequency, low amplitude vibration. Add gypsum slowly to one part of the impression. Let it flow ahead under vibration to fill details before filling the rest.
Once it's set, how do you care for the cast? Is it stable?
Dimensionally stable under normal conditions, yes.
Wow.
If you need to soak it, use water saturated with calcium sulfate to prevent dissolving the surface.
Avoid high heat,
Well,
like above 55 degrees C.
yes, high temps can cause shrinkage and strength loss.
Disinfection is possible.
Yes, using approved sprays or immersions that don't degrade the gypsum, or sometimes disinfectant can be added to the mixed water, following specific protocols. Microwave disinfection drying is still under investigation.
Okay, so wrapping this deep dive up, we've really covered the A to Z, haven't we? From capturing that intricate negative shape with impression materials
Each with its own quirks and properties.
to creating the durable, positive gypsum cast. It's so clear how linked these two stages are. The final restoration is only as good as the accuracy at each step.
Absolutely. We hit the different impression materials in elastic, elastomers like polysulfides, silicones, polyether, and hydrocolloids like agar and alginate. Talked properties, elasticity, stability, water interaction, setting, byproducts, handling.
And then the gypsum side.
Yeah.
The chemistry, setting reaction, that crucial setting expansion, normal versus hygroscopic, the 5 types based on strength and use, and all the factors affecting strength, especially that water-powder ratio.
Understanding these materials really gives you a foundation for appreciating just how much goes into making dental restorations fit and function properly.
Yeah, the choices made at each stage really matter for the patient's outcome.
Which leads to a final thought, maybe. With material science moving so fast, what's next? How might future developments change how we take impressions or make casts? Could we see even greater accuracy, predictability, maybe even simpler processes down the road?
That's fascinating to think about. What could digital scanning and 3D printing eventually replace or enhance here?
Exactly. It's a space that's constantly evolving. Definitely something to keep an eye on.